Hello, we are Bronco Engineering from Boise State University, and this is our proposal for the implementation of rooftop, carport, and agrivoltaic PV systems with energy storage for the University of Nebraska-Lincoln. This is in response to the challenge set forth by NREL as a use case in the Solar District Cup. Of our 8 members, the 5 presenting today are Ashley Rivera and Matt Zizelski for the conceptual design system, Brooklyn Andrade with the financial analysis, Daniel Boots regarding the distribution system impact analysis, and myself, Zachariah Van Deventer, for the development plan. By breaking into subgroups, we tasked ourselves with being self-sufficient members responsible for individual work completion and task management via Project Gantt chart. Meeting 2 or 3 times a week, we were able to efficiently communicate expectations and information regarding the project, thereby mitigating the presence of logical gaps.
Our approach for this challenge was to maximize the quantity of panels without placing panels in areas harmful to the production. We accomplished this by placing panels in areas of high solar access, then optimizing that placement, tilt, azimuth, and the choice of the inverter. For the battery challenge, we suggest a 750 kilowatt-hour nameplate battery. This battery will be capable of supporting critical loads for up to 3 hours at 100% confidence. We believe this is a good choice because according to Lincoln Electrical Systems, outages typically last less than 1 hour, so there is a significant buffer to protect equipment from uncharacteristic outages. This graph Hey Sam, can you go back up one? This graph shows the probability of the battery supporting critical loads versus the duration of the outage. We can see from this graph that there's a good chance of the battery supporting the loads up to 4 hours and a decent approximately 46% chance of supporting the loads up to even 10 hours.
To fully test and simulate the impact of the PV on the distribution system, it was a collaborative effort between constructing the simulation in OpenDSS and testing it with the MATLAB Grid PV toolbox. We use this toolbox to get information about energy consumption, bus voltages, and power flow. After analyzing this information before and after incorporating PV, we could then determine how we wanted to incorporate battery systems, smart inverters, and line monitors. This figure shows the minimum and maximum per unit voltages for each bus in the system over the course of the year with the given regulated voltage of 1.033 per unit. This shows that even after adding PV, there were no voltage violations, and the per unit voltage stayed within the industry standard of 0.95 to 1.05 per unit. For our sensitivity analysis, we started out by changing the regulated voltage. We tested the function of our smart inverters, and we looked at the impact of implementing the battery. We changed the regulated voltage to 1.0416 per unit to try and force an overvoltage on the system, and we tried to force an undervoltage on the system with a 1.005 per unit regulated voltage. This is critical for us to run for the placement of our smart inverters. And the last part of our sensitivity analysis was we ran our battery in peak shaving mode to simulate if the battery were charging and discharging at non-ideal times. Modeling the battery in OpenDSS had no effect on the system if the grid is up and running, since it is purely used for resiliency. The battery should never be on while the grid is on unless directly after an outage. So we also explored modeling the battery in peak shaving mode, and this models when the battery might charge and discharge while the grid is on. Output monitors were placed on our battery during our simulation to test the battery's state of charge and the power over the year-long simulation. The state of charge will show us when it is charging and when it is discharging and how the power flow is working. This analysis is useful in determining how much power can be supplied to the load if the battery were to turn on when it shouldn't be or when it's charging after an outage. After analyzing which buses were most affected from the sensitivity analysis, we began to add the smart inverter functionality to the buildings close to experiencing the over/under voltages, since none of them actually experienced that. Each bus of the system was analyzed throughout the course of the year, and we found that if we were to add smart inverters, it would be where we had carports or agrivoltaic connections. Those tend to add a voltage spike. To monitor and regulate the voltage, we initially used a deadband of 0.95 to 1.04 per unit. And using volt var control, those smart inverters will keep the voltage within that specified range. Initially, this wasn't a very useful deadband, considering the voltages never really reached those points, so we tightened that deadband gap to 1.015 and 1.025 to verify the operation and efficiency of the inverters. Next slide, Sam. Throughout our analysis, we found that there were no overvoltages or undervoltages, even when we tried to force it by changing the regulated voltage. However, we did notice a few potentially problematic buses in the system. And so if we did add smart inverters, it would be at those buses with the carport connections. Also, this wasn't necessarily an upgrade, but we did have to add a transformer to connect the agrivoltaic systems into the distribution system. And this was at the same point of connection as the College of Law. So in conclusion, even after adding all the PV, there were no voltage violations and the system was stable.
UNL's current utility price is about 3 cents per kilowatt hour with a demand charge of $16.25 per kilowatt hour of billing demand. The suggested PPA for a 20-year contract with a 2.5% escalation rate is 5 cents per kilowatt hour for the East Campus and 8 cents per kilowatt hour for the City Campus. This will yield a project IRR of 7.5% for the investors. The cost of the storage system is estimated to be $800,000. It is recommended that UNL purchases this system to protect their $2 million worth of inventory. The PV system purchase price is about $8.9 million for the East Campus and $1.9 million for the City Campus. It will cost the customer a net present value of $380,000 for East and $612,000 for City Campus for the entire 20-year contract to use the PV system. This is an estimation based on a utility escalation rate of 3%. So the price of utility in the future could increase more significantly, which would decrease customer savings from the PV system, or the escalation could be less than 3%, which could decrease PV savings. If the customer purchases the system, the investment's net present value would be $696,000 with an IRR of 13.08% for the East Campus and a net present value of $148,000 with an IRR of 11.93% for the City Campus. The customer has the option, could you go to the next slide? The customer has the option to buy out the system during the contract period at years 7, 10, and 15 for both the East and City Campus. The customer's benefits were calculated based on the assumption that the system will last for 30 years. It can be seen on the graph to the right that the customer benefits from a buyout. Similar to the East Campus, a buyout of the City Campus will result in returns, which can also be seen on the graph to the right. You're muted.
The City of Lincoln, the County of Lancaster, and the State of Nebraska have adopted both international and national codes for building, fire, energy, and electrical systems to which UNL must comply. Working closely with various planning departments at UNL will assist in adherence to the codes required for implementing the proposed system smoothly and successfully. Under the Public Municipal Zoning Code, of which UNL East Campus falls, no PV restrictions were found. While working towards obtaining proper permitting, it may prove that agrivoltaic systems are restricted in public districts. Ground-mounted systems are permissible with special use permits on ag zone districts of which the research field meets the necessary requirements for changing zones to the from public to agriculture. Once the initial surveys are completed for the proposed sites, permitting will be applied for. The procedure to do so is outlined within the Lincoln Municipal Code 20.06.120, and each building permit requires a plot plan as stated by the Lancaster County Code. Section 105.1.3 of the IFC 2012 states that under special conditions, multiple locations for a single permit may be authorized by the fire code official. This will greatly reduce the amount of time and money it will take to obtain a construction permit. There are no land use stipulations for the proposed buildings, and an erosion control plan must be created by the Lower Platte South Natural Resources District before applying for the agrivoltaic systems permit. The construction timeframe for the agrivoltaic systems is projected at 9 months. Starting the project in July, the construction and installation of the arrays is expected to start mid-January, ending in March, in time to sow the year's crops. The master plan of UNL, Plan Big, details 2 roads to be constructed, one near and one through the research field. We propose that this project should be combined with the road construction. While this may increase the logistics of the project fractionally, it will offer multiple benefits: reduce campus disruption, security measures, and access. Once the 48th Street Gateway is established, there will be no need for construction traffic within East Campus. The transmission lines can also be buried before the roads are made, which would otherwise require demolition and reconstruction. The timeline for implementing the rooftop, carport, and storage systems is expected to be 9 months. The summer months are the least busy time on campus and therefore the optimal time to perform construction. Our team proposes that the rooftop systems and carport systems be implemented in 2 groups over 2 years. This will allow for smaller campus closures and an opportunity to assess the community perception of the campus additions. As the battery storage system and the rooftop system on the Animal Science Complex are a safety measure to protect UNL's assets, these should be completed first. Gauging community interest in renewable energy systems will help with assessing potential community pushback. Our team suggests that UNL conducts continual polling in the surrounding community throughout the entire project. This will offer beneficial, real-time information on how to proceed with it. By doing this, UNL will be better established as an entity concerned with reducing greenhouse gases and advocating for clean renewable energy. Reaching out to local agricultural businesses regarding investment in the agrivoltaic systems may also provide a greater buy-in for the project. Understanding the conservative ideals that are held by many members in the community, informing the public that this project will bolster the economy of Lincoln, but also that the panels designed for use are manufactured within the United States will by itself offer backing for the community, from the community.
Now we move on to the innovation. So our design process was as follows. First, we would use Aurora to model the irradiance profiles, place the panels, and analyze losses. Then we can use this information as an input for System Advisor model, so we can do parametric optimization, hourly production, and savings calculations. Energy Toolbase was also used to explore peak shaving battery options. Lastly, with support from our mentor, Walt Novash, we used Microsoft Excel to model our resiliency battery. Our panels were selected based on their size, weight, efficiency, and sourcing. We wanted a high net CO2 reduction, so we paid close attention to the transparency from sources about their CO2 emissions. Panel parametrics were designed based on the information from Aurora Solar and System Advisor model. We utilized only 2 different product lines from SMA Solar in order to minimize intricacy and source ethically. Chosen inverters limit the inverter losses, thus maximizing our system efficiency. Our chosen battery is an LG battery, recommended by our mentors who work in the industry for their quality and ethics. Our rooftop systems are designed to produce the largest possible consumption offset and minimize our losses. As is stated in the challenge rules, energy will not be returned to the grid. Rooftop systems will cover a total of 25 buildings between the east and city campuses. Lastly, our carport panels generate useful energy from otherwise unused areas. They provide beneficial shade and cover for student and faculty vehicles, and they will be designed for 4 different lots for 3 different buildings.
We designed 4 different solar arrays for UNL's agricultural areas. 2 arrays are designed for locations the university is not currently using for a specific purpose. These arrays are intended to easily allow for agricultural activities to coincide with them in the future, and are spaced far enough apart to allow for planting equipment to be used between them. The university's primary concern is that the area can still provide opportunities for new research ventures. New crops could be planted for the area. Recommended that UNL uses the area to create a pollinator-friendly habitat, as this would provide many research opportunities while benefiting the entire community. The third area is the research field that grows oats, beans, and corn, and this system provides a great opportunity for educational research on the effects of shade and temperature. This system is high off the ground to accommodate farming equipment below the panels. The last area is the vineyards. Here, the solar panels help regulate temperature to reduce water demand. The panels in this system are placed carefully to allow for a sufficient amount of sunlight through to the crops while protecting them during the hottest parts of the day and helping insulate them at night. This solar tree, called the Curve, was modeled by Spotlight Solar. The goal of this tree is to provide aesthetics and garner public attention. It is intended to be a visible symbol that UNL is invested in solar energy. It can be programmed with a screen to display information about UNL's other solar systems. The tree will be placed near the Love Library on the city campus. For our final overview, we have a total system size of 5.6 megawatts with 7.3 megawatt hours of annual production, which will provide an offset of about 23%. Taking into consideration the greenhouse gases from equipment emission fabrication, we estimate eliminating approximately 8.2 million pounds of CO2 emissions after 1 year. Overall, our system helps with many of UNL's district goals. It helps with sustainability by lowering CO2 emissions, resiliency by protecting the animal science complex, and education via the solar tree and agrivoltaics. In conclusion, we have proposed a detailed system with diverse solar applications that is stable, has great savings buyouts, and is especially tailored to UNL. Also makes a substantial impact on the university's sustainability goals. I'd like to give final acknowledgements to everyone that helped us out throughout this project, and thank you. We'll now take questions.